these are the issues that I'm going to be discussing, in today's lecture. And I want you to keep those in mind throughout the lecture today, okay? The issue is, what is the architecture of light? Does light have an architecture? Is there an entity that underlies light? That's the only issue, okay? Now, I was going to talk a little bit about some other stuff, but I think we're going to have our hands full with this alone, based on the number of comments and questions that this individual asked. And so here we have it. Does light have a physical mediator? What do you think? I mean, do you think light is mediated by absolutely nothing? And if it's mediated by something, what is the mediator? Can we say that it's like the establishment holds, that it's transverse waves? Is that what mediates light? That's what they show you, right? And so that's one issue. The other one is it mediated by particles? The bosons. Well, we have a lot of bozos out there, but they say that it's some kind of corpuscle, and they call it the photon. They say, hey, this photon is what mediates light. Okay, a series of them, right? Okay, and then there's a third version, which is that all three of them. Okay, so we have the transverse wave, the particle, and the wave particle. Okay, so you tell me, okay, which one would you choose? Is any of these valid? Can we use any of these to simulate light? That's the issue. That's the main issue today. And one of the problems I have with these clowns, with these bozos, is that they don't understand the question. They simply don't understand the question. They say, we do math. We want to tell you something about values, about the experiments they've done, and what they proved, what they verified, what they falsified. They talk about a lot of nonsense. And all we want to understand, we want to just get them to tell us what is the mediator of light. That's the only issue today, okay? And you'll see where they hit on the corners and they never hit in the center, that question. Okay, so the only issue, again, is what is the mediator of light? So here's the question, okay? What is the mediator of light? And here you have all these different versions. We have the one-way discrete particles. I put Alhazen, I think that's how you pronounce his name, Alhazen, I call him. Anyways, Alhazen, I think he was 11th century in the Arab world. And he's the one I credit with the particles, not the Greeks, because the Greeks thought that it was like Superman's vision, that the particles emanated from Superman's eyes and go through the wall. And Alhazen said, no, whatever you see, it's sending particles to your eyes. So that's the only reason I credit him. But, it's just history, just so you know which one is which. Then we have the transverse wave. The waves were created by, what's his name, Robert Hooke in 1665. But it was Fresnel, French guy, who, beginning of the 19th century, he's the one who really came up with this notion of the transverse wave, trying to explain, with his picket fence, he tried to explain an experiment. Anyways, when he had proposed the transverse wave, Maxwell comes a little later, a few decades later, and he mathematizes this transverse wave. And that's what we have today, or at least what quantum has today. Then you have the one-way packets. I credit Penrose here. He's the only one I've seen that drew it in one of his books. Okay, so I use his wave packet, even though the notion already existed before him, right? Then we have the ether version, and also I think the flat earthers pretty much subscribe to this, that there's some kind of vortex out there. One of the proponents of this was Rene Descartes, but I'm not sure if he's the first one to propose it. Anyways, there's these vortices, right? And exactly how that works with light, I have no idea. Okay. And then you have my version, which I'm saying all these years what they've mistaken the transverse wave is with a rope-like mechanism or entity that torques. That's the mechanism. And so there you have the different versions that you can choose. If you have some other version, by the way, there's people also proposing that there is nothing underlying light. And so, if you have another proposal, hey, you're welcome to propose it. And before you can call any of these irrational, you have to define what you mean by irrational. We do define it in this site. We do rational science, so we better know what rational and irrational is or means. And we're saying that irrationality is when you reify a concept and begin to move it around. You turn it into an object. Again, like field or energy, right? Wave. And also another criterion is failing to define the key words that make or break your theory. Those are sine qua non. You need to have definitions. And a lot of people think that when you define words, you're doing semantics. And that's another thing you should keep in mind today, okay? Because that's the official version, that when you attack them from a language point of view, that you're doing semantics and you're not doing math, you're not doing physics, etc., right? And yeah, what we're looking for is physical interpretations, mechanisms. For that, you had better have your language straight. That's the way we look at it here. And again, the third one there is the proposed mechanism is unimaginable. Then you have an irrational theory when nobody can imagine it. Like moving through the fourth dimension. Yeah, try that. Okay, so these are the things to keep in mind, okay, throughout the discussion today. It's going to be a dialogue because I'm going to present what they asked or what they commented on, how I'm going to answer that. This bozo criticized my notion of stopped light, the fact that they claim to have stopped light. And yeah, you can see why he's a clown, because again, these people don't understand. They just don't understand physics. They say, look, they ran an experiment, they proved that light could be stopped, and blah, 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 blah. We have evidence, it's been falsified or verified or whatever. They talk about nonsense. They talk about experiments and proof and evidence. They don't talk about mechanisms. And that's why they never understand the question. And when I come around with the question, they say, what are you talking about, Bill? You lost me. Yeah. And so here, let's present the question as I presented the other day, and this is what he answers. Claims that light cannot slow or stop. And so we need to put it in the proper context, okay? The irrational mathematical version is that the mediator of light consists of one-way mathematical waves or magical particles. That's the official version, okay? We're talking about quantum particles, mathematical objects, as they call them, right? In other words, they don't act like what they call classical objects, meaning rationally. They can be, two particles can be at the same place at the same time, which is not true for what they call classical particles. That's the issue. So they have all these weird Alice in Wonderland properties, and they call them quantum particles or mathematical objects, and they try to get away with murder because what they're introducing is irrational concepts. That's what it is. That is what the rope model challenges, the mediator used to explain the properties of light. Little c is a constant, right? C equals frequency times wavelength, right? Constant means that c does not change value, but that when frequency goes up, wavelength goes down. That's what the little c stands for. You can't change little c. These people try to do that at all times. And so we have light traveling at this speed. If you want to change that, little c and put 0 there, which would be a constant, which would mean that light is not moving at all, well, either lambda or frequency have to be 0. One of the two has to be 0, or maybe both. But at least one of them has to be 0. Otherwise, you can't get c to go down to 0. Okay, so keep that in mind. Light on the red end of the spectrum is invisible, not because it's slowed down, but because length is longer. So we are beyond the range of what they call wavelength, meaning length of a rope, right? And there are fewer links per unit length. That's what the equation stands for. That is the equation of a rope. If we manage to freeze atoms in a region so that the electron membranes do not expand and contract, meaning quantum jump, right? The electromagnetic ropes between those atoms will not torque. That's what it is. You don't have any torsion. So if you can freeze the atoms and they don't pump, they don't expand and contract, you've frozen quantum jump, right? Then the rope has no chance of torquing. Light has stopped. Not because one-wave photon balls have been frozen in midair. Light has stopped in the sense that the atom is not pumping torsions to your eye. Okay? So let's see if we can understand what all that means. Okay, we're saying that we have this little equation called the speed of light, little c. It's a constant. It's equal to frequency times wavelength. And here you have frequency times wavelength. Okay, there it is in a rope. Okay, the number of links, frequency. How long each link is, wavelength. Okay, and when one goes up, the other one goes down. Here we have more frequency, more links, and each link is shorter. And here you have, the opposite. We have the links are longer and we have fewer links. That is the equation of a rope. Maxwell's equation is not an equation of a wave or of particles, series of particles. It's a wave. It's an equation of a rope. The rope is the only physical object that can simulate Maxwell's equation. So those notions that people have that we left classical physics behind because we could not explain anything, it's because you simulated everything with particles and waves. That's why you could not explain anything in quantum mechanics. Period. That's the only issue. Okay? Why can't you explain? Because you never defined what an object is, and you're using concepts as objects, you're using fields and energy as objects, etc. You're using abstractions to do physical interpretations. And abstract is the opposite of physical. And we're doing physics, we're not doing abstraction, so we're not abstracists. We are physicists, the opposite of abstracists. Okay, so here we have the stoplight. This is the answer to him. The claim of irrational mechanics is that light is stored in the medium. So they're saying that they're going to freeze a little piece of region of space, right? They're going to freeze whatever's in there, meaning atoms, right? And because they froze that, suddenly they froze the photons of light which were flying between those two atoms. So we have these two atoms, right? And the photons which are between them are frozen in midair. That's what they claim, that they froze light in the medium. Yet we can see the light trapped in there because, why? The atom is pumping that light to our eyes. Now, if you don't believe in the rope, no problem. You don't accept the rope, no problem. But under the quantum version, it's quantum jump, motion of the electron back and forth, closer and farther away from the nucleus, that generates light, the energy coming out of the atom, as they call it. Okay, so even if you go with quantum, something is moving in there, and that's why you would be able to see. If no quantum jump takes place, there would be nothing to see, because now you're not receiving energy or frequency or wavelength from the atom. Okay, so if we can see the light, then light has not stopped. If you can see a little bit of light in there, light has not stopped. Even according to the religion of quantum, light is generated when the electron rises and falls from energy levels, right? If the experiment receives light from the frozen region, an atom from inside the region is sending it to his eyes. Okay? Therefore, the claim that the experiments have stopped light is a lie. Meaning, right? Let's say it scientifically. The forgers have once again falsified their results. That's what it is. Stoplight should not be visible. That's the bottom line. Okay, so here we have the experiment. I think this is the original experiment. This was done in 1998 or 1999, okay? And I think it was this lady who did it in Harvard. So listen to her. But this is the introduction to what she did later. The fellow who does the reporting, he explains it first. So listen to him first. Okay, here goes. So he's going to explain what they did as far as the experiment. They're going to freeze the atoms in this ultra-cold region. Okay, here goes.
Lena Howe created a cigar-shaped Bose-Einstein condensate to carry out her experiment. She fired a light pulse into the cloud. When the pulse hits the condensate, it slows down to the speed of a bicycle.
Okay, so Light goes to the condensate, this cold region. Okay, you don't have to know any fancy words. You essentially send light and somehow freeze that region, and light gets frozen. Okay, and you saw how the light comes in. Now listen to her, how she freezes it. Okay, this is the lady who supposedly came up with this. Okay, here goes. Listen to her.
So light pulse might start out being 1 to 2 miles long in free space. It goes into our medium, and since the front edge enters first, that will slow down. The back edge is still in free space. That will catch up, and that will create that compression, and it'll end up being compressed from 1 to 2 miles down to 0.001 micron or even smaller than that. You could say, well, we just set a laser beam into a wall and I would stop it. Well, the problem is you lose the information because it turned into heat. You can never get that information back. When we stop it, the information is not lost because that's stored in the medium. Then when we have time to revive it, the system has all the information to revive the light pulse and it can move on.
Okay? So what's the issue? The issue is they're shining a light to this region and they freeze light, but you can see that there's a little light there. Why can you see that light? And so let's go in steps here. Let's make sure we understand how light is generated, not according to my theory. Let's go with quantum. Let's go with their version, okay? Okay, here it goes. There's your atom, right? This is the atom created, the planetary model created by Rutherford and Bohr. And they've modified it nothing really in the last 100 years. They say that it doesn't orbit like that. It just bounces around different areas in the region called an orbital. So it doesn't matter. Here we made it smooth. It's just not smooth. That's all you got to think about. But the point here is when the atom falls to a lower energy level, it releases that green arrow, which is energy, which is light. And when it rises, apparently it does so again. Okay, so it's constantly falling and rising, and by doing that quantum jump, that's what creates light. So something has to be moving in order to create light. If you were to freeze that electron, there would be no light according to quantum mechanics. Okay, that's not me, that's according to quantum mechanics. So let's get that right. Okay, so this is the official version. Now, here's what this lady showed. Okay, she showed this. And you see that little light there, and you say, hold it, I can see a light there. Why am I seeing the light? I should not be able to see anything. Okay, but they say, look, we can see the light. We've frozen light right there in that region. Well, we have a problem because, here, let's illustrate that. You have all these atoms pumping these torsion waves, transverse wave to your eyes. Why am I seeing that light if light is the back and forth, the movement of the electron back and forth from energy levels or orbitals? So something is still moving in there if I can see that red light. Otherwise, I wouldn't see the light. I wouldn't see that red light. And just in case, here it is up close. Okay, so that's what it's doing. It's got the atom has to be pumping. Okay, like I say. The electron has to be moving back and forth between energy levels to create those waves or particles. I mean, I could replace the waves with particles. We're in the same boat. Okay? Or I can replace them with ropes, electromagnetic ropes, as we say. And same thing. In other words, whatever you replace it with, that means something is moving in there if you see that light, if you see that red light. Okay, so we have a problem here because, these people are saying you can see the light, but we stopped light. So what do you mean? What is that you stopped? I mean, obviously, if I can see the light, something is moving in there, and you haven't frozen light. If you freeze light completely, you shouldn't see anything. That's the bottom line. So no, we cannot stop light at least if you see that, right? But under the rope model, assuming you could freeze the atoms from pumping. See, remember how this works. You have the two atoms and my fists, right? And they're expanding and contracting. They're doing this, right? Expanding and contracting. By doing so, they torque the rope. Okay? Now, assuming we could freeze the atoms so they're not pumping anymore because we took them to I don't know, 0 Kelvin or whatever. Okay, so we've got very cold region. The atoms are not pumping. Now the rope is not torquing. That we can understand. But then we should not see anything. Because light does not come from the rope to your eyes. Okay, you're not going to see light. You're going to see the atoms which are sending light to your eyes. Light comes from atoms, not from rope. You can't have a rope coming from the middle of another rope. The rope comes from the atoms. So if the atoms are, standing still, then they're not pumping torsion waves to your eyes. Just that simple as that. So you should not see anything any old way you look at it. That's if we can freeze atoms to the point of them not pumping. But then if, like this lady says, that she was able to freeze light, well, did she? I mean, if light is coming to my eye, something is pumping in there. So obviously she's got a contradiction that she hasn't resolved. But they were quick in publishing it. They said, oh, this lady froze light. Yeah. Okay, and there's another issue we need to solve, and it's one that we're going to take as homework for everybody, okay, anybody who wants to deal with it. And that is that we were talking about why light travels straight. Okay, and we're going to try to answer this question probably next week. Okay, today was just beyond the scope of the class today, lecture, right? But the question is, can you see light backwards? When light goes through, it's really going through a bunch of atoms in air. That's why you see the reflection. Like when you see light sideways, right? A beam of light, such as a laser pointer, a strong laser pointer, and you see the red light, for example, right in front of you, like a straight line. Why are you seeing it? Well, because that light is stimulating every atom that's in that line of sight, right? If you were looking through at the same parallel to the laser. But why can you see it perpendicular? Because it's sending light to your eyes through all the atoms in the air that are connected to your eyes. That's why. Okay, so you need a mediator in order to see. You need atoms for reflection or refraction, right? Or diffraction, if you, any of them, right? You need a mediator. If there's absolutely nothing, you would not see it sideways. The only way you can see sideways is something, if there's an atom there that is relaying, light to your eyes. But then what happens when you're behind the laser, right? Can you see it from an angle? Yes, you can. You don't see it as good as if it's the laser's pointed directly at your eye. So it's much more intense going into your eye if it goes straight into your eye than if you're seeing it from the side or from an angle. And the question is why? Doesn't every atom along the path send light in every direction? And this is the same for any, I don't care if you believe in quantum mechanics, you want the rope model, anybody has got to answer this question. Why does light come out of an atom in every direction, right? Because it's doing this quantum jump. And why can I see it more in the direction in which the light is being sent, right, by the laser than from the side, from an angle? Okay, so that's the issue. That's the question in front of you. And so here, I'm going to show you what I'm talking about. Here you see light going out there from a source to some target, okay? And the question is, you have this light going in every direction. I only put 2 atoms there, right? Any atom in there, it will send light in every direction. Backwards, for example, or frontwards, but not along the main beam. And so the question is why? Why do we see less of the light behind than in the direction in which the beam is pointed at? Okay, so that's the $1,000,000 question. Okay? No math. Just answer the question, right? We don't want any equations. We don't want any numbers. We just want to know the physical cause. Why? I think I have. Here's my laser pointer. Here you have light. Okay, I hope you can see that. Okay, and so the question is, you can see that there, but see sideways you see much less. Not as brilliant. And the more I turn it, the less you see. It's there that you see it a lot. And the question is, why do you see more in the direction of light and not to the sides? If every atom along that beam, right, along the ray, every atom there is shooting light in every direction, is relaying the light in every direction. refracting it, reflecting, etc., right? Why shouldn't you see the same amount? And that question again is for quantum, whether you do waves or particles, or for the rope. For all proposals, the question stands.